I am Jamie Neeley. I work with Seth Stein. If you haven't met me yet, I know a lot of new people here, so nice to meet you all. So what I study is I focus on earthquakes. And so what I've spent my summer working on is building a better earthquake model. And the idea is that seismologists, as much as we want to, we cannot predict earthquakes. We cannot tell you where the next, like when the next earthquake is going to happen. So instead, what we do is we issue earthquake forecasts. And the idea here is we say, okay, the probability of an earthquake in this region is X% over the next 30 years. So in one region we've been looking at is Southern California. So just to give you a sense, along the Southern San Andreas Fault, there's a 52% chance of an earthquake greater than magnitude 6.7 in the next 30 years. This is sort of one of the recent studies that came out. So the question is, how do they come up with this number, and is there a better way to do it? So that's what I've been working on this summer. So it really boils down to sort of three easy steps to calculate earthquake probability. The first is you gather paleoseismic data of past earthquakes. So here is a record of earthquakes along a certain section of the San Andreas Fault. Then you match a probability model to the distribution of inter-event times, so the times between the earthquakes, and then you can calculate the probability of an earthquake. Seems pretty simple. Obviously, there's a lot of uncertainty that goes into this. Sort of the dates, how do you choose the right model? What assumptions do you apply to that model? But yeah, that's sort of how they're coming up with these earthquake probabilities. But there's some major problems with the current way these are calculated. The first is that the probability of an earthquake doesn't always increase with time. So if you look at this plot here, this is showing the probability of an earthquake occurring in the next year. And 1857 was when the most recent earthquake occurred along this part of the San Andreas. And you can see here that, initially it increases a lot. And then as you move on past today, the probability actually starts to decrease, which is a problem. You wouldn't think that the probability of an earthquake would decrease. The other is that these probabilities are only based on when the most recent earthquake happened and don't actually incorporate any additional information regarding the ordering of sort of how the previous earthquakes occurred. So what we've done, many of you know Leah Saldich. For the new folks that you don't know, she was also a lab mate of mine. She developed this model called the long-term fault memory model. And what I've been doing this summer is reformulating this model as a Markov process to actually calculate better earthquake probabilities. And so what we can actually do now is the LTFM is great because we can incorporate additional information about the history of the earth, about the actual earthquake histories, and it better reflects sort of the processes that go on. And we can see here this plot is showing how today the earthquake probabilities are about the same, but moving on to the future, our LTFM model compared to the other ones indicates that the earthquake probability is much higher than what the other models would assume. And by 2150, our model predicts the probability of an earthquake about 1.6 times the other models. Thanks.